I would like to thank all the speakers for accepting the invitations, especially for those who accepted the invitation in the very last moments. We have more than 90 registered participants, so I hope that the discussions after the talks will be fruitful. Second speaker, Laurent Daudet. I'm sorry about my pronunciation of French names. I hoped Thibault would be here on time for introducing, but he's not here yet. Laurent is a professor of physics at University in Paris, and um, um, he in 2016 he co-founded Light-On, a startup devoted to large-scale AI originating in photonic computing. And with this, I would like to give the screen to Laurent.
Thank you for giving me the opportunity to present the work that we've been doing first in the lab and then at Lighton, this optical computing startup, and that became a generative AI company. I will explain the also the journey of the startup that has been quite nonlinear. Uh, so yeah, Lighton today is it's a spin-off from university research. So we are four co-founders, including Igor Caron, who is now the CEO of the company, and we are three university professors. Florent is an expert in machine learning. Sylvain is expert of optics and photonics, and I'm an expert in signal processing. So the team itself is nowadays about 45 and 50 now, I believe. And we are based in Paris. So yeah, there's always this idea that when you create a startup, you have a clear idea of where this is all going. But actually, it all started with a lot of serendipity, I would say, lots of coffee, lots of procrastination, and meeting, and just by chance we discovered what would be the starting point of the company. It was all in the photonic lab of Sylvain. He was doing some computational imaging. So computational imaging is this idea that if you put algorithm machine learning on top of photonic experiment, you can improve, like you can do super resolution, you can do all this type of nice thing. And we were looking at this experiment, and we realized that with this light scattering operations that were done in the lab, we could perform some mathematical operations that are useful for computation in machine learning context, and that we can just harvest. I will explain what I mean by that. So this it all starts with this idea of a light scattering in free space. So yeah, just to be very clear, we are not doing integrated photonics. We are doing free space optics. It has some pros and cons. I will detail later on. So if you have some scattering material in the middle here, you can see the scattering material. It could be something as simple as a layer of white paint, for instance, and you have some coherent light, like a laser, shining on this material. Then what you see on the screen is a speckle. A speckle is just the resulting of interference of the wave. All the At the output of the scattering material, there are secondary sources that interfere uh, co- um, uh, constructively or destructively on the screen, creating this pattern, the speckle. And if you can generalize that if you use some special light modulator, which is typically the device you would have in video projectors to modulate spatially the beam to impinge an image basically on the beam. And then you have a CMOS camera here. This is just a generalization of the previous experiment. For each different image on the spatial light modulator, you would have a different speckle. What you have to realize is that the spatial light modulator is a discrete input vector. You have, say, 1 million pixel here, and the CMOS camera is also a discrete output vector where you measure the speckle intensity. And since the light transmission is linear, you must have a linear system. You must have some transmission matrix H that controls everything that you have between the input and the output. And this transmission matrix is random due to the randomness of the material. And what you measure at the output, Y here on the CMOS camera, is the input vector multiplied by the random transmission matrix. And then you have the element-wise nonlinearity. You take the intensity because the sensors they measure the intensity of the field. So you have this big this big matrix vector multiplication that you have for free due to the light transmission in the scattering material with random coefficients. In practice, how you do that, you have a laser shining on the light modulating device. Here you can use what's called a DMD, digital micromirror device, where you have millions of small mirror where you can decide to they are binary intensity modulator. You can input the image here, and then you have the light modulated image going on the scattering material, going on the camera to record the speckle. So this is where you input the data, and this is where you output the result of the computation. And note that the computation itself, which is like multiplying by the random matrix, is done by the scattering material in a very passive way. So it's computation without energy input. You only need energy for the laser, for the light modulation, and for the camera, but not in the scattering material. And what is the real strength of this free space optics is that you can do really very large scale already. So the scaling is not a problem. Typically, in the light modulating devices, you have millions of independent input pixels. And again, on the CMOS camera, you have millions of pixels. Now you have sensors that have many, even 100 million pixels. So the resulting transmission matrix is absolutely huge. It can have 1 trillion of random coefficients. And if you manage well the optics, they are really independent and identically distributed complex Gaussian random coefficients. So this is the equivalent of terabytes of memory. Note that these coefficients are fixed by design, and we are in the non-Feynman computing. You cannot design these coefficients, but you can just leverage the big size of these coefficients. So how do we use this random projection multiplying this random matrix? Well, there is this well-known mathematical fact that's the Johnson-Strauss lemma that says that random projections, they are distance preserving embeddings. You can use random projections, for instance, to reduce the dimension of vectors and they will still keep approximately the same angles that they have between them. Or you can expand, embed in a larger dimension space to be able to make easier linear separation, for instance. And this is well known in the machine learning community. You can approximate some kernel with these random features. So we started really from a lab experiment and in 2016, and over the last few years, 2017, 2018, 2019, we just climbed the ladder of the TRL scale, trying to validate in the technology in relevant environments. So what we did is to design this what we call optical processing unit, OPU, and I believe at that time that was the world's first photonic AI coprocessor that was publicly available in 2019. The idea is we could have like peta-ops type of scale in terms of number of operations. Again, it's not a one-to-one comparison with a CPU or GPU because they are non-programmable coefficients. So it's a bit of a different type of operations, but still it's huge. And with only 30 watts of power consumption, which was at that time 200 times better in number of operations per watt than what were state-of-the-art GPU at that time. They were NVIDIA V100. So very low power consumption, very high number of operations. Uh, we were quick to put it on the cloud so that we could have AI researchers using that from all over the world and build a community of use cases. In terms of optics integration, we worked a lot on how to go from the optics table to something very compact. The size of the the photonic core, as we call it, was about the size of my smartphone. Um, Very, very integrated. And we all integrated as well in a hybrid data processing architecture. You could use your favorite PyTorch Python programming and just have some specific API to connect to the optical processing unit, just to do some hybrid computing. The goal is not to replace, of course, a CPU or GPU, but the goal is to offload some of the very large computations to the OPU and go back and forth between these three components, CPU, GPU, and OPU. Uh, in terms of software, I put in the middle a few schemes where we use the optical processing unit in a hybrid scheme. Randomized SVD is something that we do. We use the OPU to do um, dimensionality reduction before randomized SVD. Transfer learning, in that case, we use that for dimensionality expansion. Reinforcement learning, we learn to play games with this, and we use the OPU in the feedback loop. Sketching for change point detection. Again, we use the randomness of the operation to allow a good detection on change point detection for very high dimensional signals. Here we use that for in molecular computations where you have to detect the change of configuration in a molecule, here for the SARS-CoV computation on the reservoir computing, and I'm going to skip these two details, but you can leverage the randomness to do what's called adversarial robustness or the differential privacy of the computation. I'm just going to detail just one type of example, which is accelerate scientific computing with randomized numerical linear algebra. This is something that's well known, that you can use randomized algorithm that are, I'm quoting an article here, DOE report. These randomized algorithms are essential to the future of computational science and AI for science, because most of in many cases, if you go to very, very high dimension, you cannot do your standard linear algebra computations. You have to use randomized computation. Uh, so just to give you a hint of how we can do that, this is a very toy example. You have to multiply two matrices. As a caveat, don't do this in practice. This is a very bad approximation, but just to give you the idea. So you can approximate the multiplication of these two matrices by inserting a random matrix R, which is like a tall matrix. And you know that with a random matrix, if R is random with ID Gaussian coefficients, R times R transpose is approximately the identity matrix. So that's why you can insert it between A and B. But then you just compute AR, which is a compressed version of A by the random matrix R, and R transpose B is a compressed version of B. And then you can just multiply AR by R transpose B to get the approximation of the result. And the idea, of course, is to use the optical processing unit to do this compression of the matrix for free, very, very fast using the principle I've just explained before. So the idea is really to reduce the computational complexity of this matrix vector or metric matrix multiplication. Another better example is approximate some trace estimators, and you can do that for it's important for graph neural network. For instance, in network, you want to detect how many communities you have. It may be like, for instance, social media. You want to see subgroup in like in Facebook group of users, and counting the community. Uh, um, it's like counting the number of triangles. And counting the number of triangles is related to the trace of the cube of the adjacency matrix of the network. So this is very, very involving in terms of computation, because if the network is very large, say you have 1 million users, or even trillion of users for Facebook, you sometimes you cannot compute the cube of the adjacency matrix. So what you do is to use some tricks like Hutchinson's trace estimator, where you can also compress the adjacency matrix left and right with a random matrix on the trace of the A cube is approximately the trace of R A cube R transpose, which is um, the trace of the compressed matrix to the cubic value. So this is a huge computational gain because you now you can compress the matrix to such a size that computing this cubic value is tractable. And here you can see on the graph on the right, uh, given the compression ratio, what is the relative error? So if you tolerate 15% error, you can compress by a factor of 10, for instance, the size of the matrix. And this is quite useful in this community detection in networks. Singular value decomposition as well, you can do SVD. So let's say X is a matrix. You want to compute the singular value decomposition, USV. But if X is too large, you can compress again X with some random matrix to have an X hat randomized version of the matrix, compressed version. You do the SVD of X hat, and then from there you can recover the approximate version of USV. So this is of course an approximation, but it's a controlled approximation. You can compute some bounds on the error. Uh, and yeah, this is just a few benchmark classification. We were comparing computation time on GPU only or GPU plus light on OPU. So in some range of parameters, we can get 20 times saving in terms of speed and a lot of saving in terms of energy consumption. Yeah. The we were doing this type of uh, integration and computation until 2020. And then in 2020, there was this GPT-3 model that came out from OpenAI. And that was really the time we were looking for application of very large scale AI. And training a single GPT-3 model required 3 million GPU hours on a huge carbon footprint, of course, and also quite expensive just to train one model. Um, at that time, I think as Microsoft had built the world's fifth largest supercomputer just for OpenAI. And the question we ask is, could the OPU technology speed up the training of a large language model? So we learn how to train this model, uh, and we put an OPU in one of the supercomputers of France. Uh, I think this is to the best of my knowledge, it was the first time an optical photonic coprocessor was put in a supercomputer. So Jean Zay is France's largest research supercomputer located near Paris. So this is a picture of the supercomputer in one of the racks here on the right. You can see the optical processing unit on top of racks of GPUs. Um, so we learned how to train a large language model on GPUs, and there was an immediate market for it. So we had to pivot the company and focused on training LLM, large language model, and split really the focus of the company. Uh, on the software side was going to be really focused on the training large language model. On the hardware side, was back to R&D and even back to the lab. Um, the company now is just a software company doing large language model trained on GPU. We have trained a number of open source LLM, contribute to the community. Our latest release was Modern BERT, which is a replacement of the famous small language model that is BERT. We partnered with Abu Dhabi TII to build the world's first large language model in standard Arabic. That was called Noor at that time, 2022. And now Lighton is in 2025. As I said, we are focused on a large language model. We do that on the standard NVIDIA GPUs, so no more optical processing unit. And our mission is to turn generative AI into an enterprise-ready solution, which is a LLM platform for the enterprise. And now it's completely deployed with some of our clients. We want to take this technology of large language model and make it something enterprise ready, safe, reliable, compliant, customizable, and sustainable. So I mean, I'm not going to go into all the details on what we do, but we make it as a product that large companies can use and enjoy uh, on their own platform. So typically, we do what's called a RAG, which is like you upload a set of documents and you ask questions, you ask some insight to a set of documents, and the system will give you an answer based on documents that not that the documents can have some graphs as well to and we even extract information from this document. We do also more complex workflows like what's called agents. Now, agents can execute different tasks like here OCR, execute some Python code just to to do some complex task given a graph here. And finally, uh, in the lab, we continued the research, and we were wondering if we could use optics to train some very large digital model. And so back to the lab, we we used a scheme to replace backpropagation in the training of a large neural network. Backpropagation is the standard scheme for training. Everyone is using that. Um, one of the issues with backpropagation is that it's uh, inherently a sequential algorithm. You train layer by layer in a backwards way. You backpropagate the error and you tune layer by layer based on local gradients. But you can replace this scheme with a different scheme that's called a direct feedback alignment, where instead of training the layer by layer, you can input the error function here, and you can input that using random projection um, to every layer in parallel. And that's called direct feedback alignment. The original paper was published in Europe a few years ago, and we have shown that we can replace the gradient signal from the layer above from back propagation with some random projection of the gradient uh, of the error signal. You only have one error signal, and you the output of the network, and you input all the error with some random projection to all the layers, intermediate layer, and so you can do the update in parallel, which is a big gain in the speed. So we use optical DFA, optical direct feedback alignment on the text transformer. Can we train a language model uh, with some optical processing unit? Our neural network has 1 billion parameters, which is like medium size. Of course, it's not as large as the full GPT-4, GPT-5 that may have hundreds of billion of parameters, but it's still a reasonably large transformer. And out of this 1 billion parameter, about half of them receive the optical signal directly. And we used some small corpus of movie dialogues to train the model. So what are the results? Here you can see in terms of the loss function compared to the number of processed tokens. The dark blue line is the one with optical DFA. So what is interesting to note is that it does train. Actually, we can see the result of the training at the beginning. Of course, it's just the output is just completely random, and then at 20% training, the words start to form, still quite a few mistakes. And at the end of the training, so it makes some actually some proper words. The words are correct. The meaning is not quite there, but there is definitely some training. It's slower in training than backpropagation in terms of process tokens, but still it does train. So it trains. The result is okay-ish, but not amazing, but it's still slower than the GPU and large language model. Uh, we considered another task that was more suitable for optical direct feedback alignment, which is a vision task on some weather forecast, climate bench uh, type of maps of the world. So this is a vision transformer now, 134 million parameters. Um, and we can extract the surface temperature change, predict the future based on the partial differential equations. And so I'm going uh, to skip the details, but what is interesting to note is the optical DFA works. It gives better result than the standard backpropagation in this context, and it's close to state-of-the-art performance. It's still slow, and the random projections are too small. Uh, Here, if you compute the training time per sample as a function of the dimension of the hidden layers, you have to go to very large size to get some computational advantage. Here you can see only on the top right, the ODFA becomes faster than the backpropagation, only for very large size. But the scaling goes in the right direction. The scaling tells you that the larger the transform, the better, the quicker it is in terms of the scaling, the going through the optical network can give you a photonic advantage in terms of computation. Again, number of layers. Only in the very large number of layers, there can be some advantage. So yes, the take-home message is that the direct feedback alignment is a parallel process, parallel with regard to the number of layers. You can update all the layers simultaneously. It has the potential to outperform backpropagation for large models, for very large models, but you really have to push it to the extreme to see that. So by way of conclusion, I have a conclusion here it's not photonic computation. You can do photonic computation two ways. You can do integrated photonics. Integrated photonics is very fast, but the challenge is scaling. The other avenue that we took here is to do free space optics, and free space optics is slow. It's fundamentally a slow process. We were working in the kilohertz regime, so which is pretty slow for this type of computation, but it's extremely large scale, and scaling is not an issue. So there can be pros and cons in both techniques. In terms of a startup company, yes, no. Lighton is the first publicly traded generative AI company in Europe. We did our IPO just a year ago at a rather early stage, but surfing on the wave of generative AI. And in terms of yes, technology, is now working only on the on NVIDIA GPU, no more photonic computing, but still, I think it's an interesting entrepreneurial journey that has led us um, to where we are now. Of course, the entrepreneurial journey is not linear. We started as a photonic computing and ended as a purely software generative AI company. But I think it's a good example of what you can achieve if you are adapting to the market. And by that, I will stop my presentation.
Thank you so much, Laurent. Very interesting talk. I wanted to have this understanding thanks to you for some years, actually.
Thank you.
Dear audience, welcome here again after a short break. I would like to introduce our third speaker, who is Łukasz Lassablière, who holds a PhD in ultra-cold molecular physics, where he focused on control of ultra-cold dipolar molecule collisions. He joined Pascal 4 years ago, and he will speak in this direction, introducing the company and quantum computing with neutral atoms. Screen is yours, Łukasz. We are ready for your talk.
All right. Today, I will give a talk about how we can do quantum computing with neutral atoms. So indeed, my name is Łukasz Lassablière. I'm working at Pascal for 4 years now. So I will try to introduce our technology. And basically, I have decided to split the presentations in 3 parts. So the first part is how can we do quantum computation with neutral atoms? So the second part will be a bit more dedicated about why do we need quantum error correction to target FTQC and what does it mean for neutral atoms. And at the end, I will explain about what does it mean to build neutral atom quantum processor units. So I will say QPU during this presentation. It's just a quantum processor units because I want to highlight the fact that it's quite different building an experimental setup in a company compared to, for instance, an academic lab. First of all, I just want to highlight the fact that there are 2 main ways of doing quantum computing that I will try to explain here. So the first approach is what we call digital quantum computing. So the idea is very simple, is that you will digitize your complex calculation into elementary blocks. The idea is quite similar to what is done on your laptop, or basically, if you have a complex calculation, if you are able to digitize it in terms of addition, subtraction, multiplication, and division, you are able to perform a calculation. And this is very similar in digital quantum computing, where here our elementary blocks are called quantum gates. At Pascal, we can do single qubit gate, 2 qubit gates, and so on. And I will detail a bit more later in the presentation. I think it's also important to highlight that there is another way of doing quantum computation with atoms. It's what we call doing analog quantum computation. And the idea here is quite different. So the idea is that we will perform a global operation on all the atoms at the same time. So this operation is described by an Hamiltonian H. And finally, the Schrödinger equation that will describe the dynamic of your system. And the idea is that if you are able to map a concrete problem on this Hamiltonian, just letting the system evolve and performing some measurements, just solve naturally the equation that you want to solve. In practice, this approach is non-universal because the you are a bit limited in your system, but what is the kind of Hamiltonian that you can produce? But in fact, it produces better performances than the digital approach in the short term, because you are much more or less sensitive to noise. Because what I don't say just before is for the digital quantum computing, when you try to digitize your complex problem into a sequence of gates, basically your calculation will be a sequence of thousands of millions of gates. So if you have a small imperfection, if one of the gates, basically you will accumulate this error a lot of times. So you are quite very sensitive to errors, and we will see this in the next of the presentation. But on the other hand, this approach is quite interesting in the long-term path because it's a universal approach in the sense that you can solve any kind of problem with this approach. So at Pascal, we work with the technology of neutral atoms. So our qubits are atoms, and we will encode the information into two electronic states of the neutral atoms. More precisely, at Pascal, we focus on the rubidium atoms. As you can see, it's an atom that is in the first line in the first column of the periodic table. This means that this atom has only one valence electron. So this atom is very similar to a nitrogen atom. So this atomic structure is quite simple, well-known, and the transitions that are needed to perform the different transitions that I will show later, we have some commercially available lasers that are quite powerful at those wavelengths, so that's why this atom is quite interesting for us. So to perform a calculation, what we need is that we need qubits. And how do we have qubits with neutral atom? The idea is very simple. We need to trap atom in a vacuum chamber, and this is how it works, basically. So we have a vacuum chamber here that is represented in gray, and the idea of this vacuum system is to perform a very good vacuum. So what do you want is that you don't want residual gases inside. And what you will do after is that you will put some rubidium atom inside, and you will try to trap an atom with what we call an optical tweezer. An optical tweezer is nothing else than a light that is tightly focused. So how do we do it? It's very simple. We send a light that will enter in the vacuum chamber. This light will be focused in the center. And if you choose correctly the wavelengths and the intensity, you have what we call an induced dipole force that will push the atom in the region of highest intensity of your light. So you are able, in principle, to trap only one atom per tweezer. And this is basically how it works. So, but how do we know if there is an atom or not? The idea is very simple, is that we will add an extra laser that is not represented here, where we will excite this atom into an intermediate state with a very short lifetime, the order of 20 nanoseconds. And the idea is that we will keep this light on. And basically what will happen is that your atom will be excited, it will emit a photon, and then you will have many cycles like this. So you emit a lot of photons, and all those photons can be recaptured back. You will pass through the lenses, and we just put a camera so that at the end we are able to see when there is an atom and when there is no atom. And this is more or less the signal that you see here. Here you can detect that there is an atom because we collect a lot of photons. Here we don't have any atoms. And this is more or less what is needed to have one qubit in your system. But the idea of quantum computing, as you know, is to do calculation with a lot of qubits, because with one qubit, we can't do much. And the idea also is quite simple. So we need to have a lot of atoms. And the point is that we can't, okay, if we want one atom, we use one laser, but we don't want, if we want, for instance, 1,000 atoms, we don't want 1,000 lasers. So we use an optic trick that is very well known for decades now. So we send the light through what we call a SLM. So this SLM is a spatial light modulator, and the idea is to print a spatially dependent phase on the electric field via this device, so that in the focus plane here, this translates into a spatially dependent intensity. So this device helps you from a single beam to generate multiple beams at the same time. So this is what you observe here with a single bit. We were able to produce 16 beams. And this technology is quite interesting because we are, in principle, able to generate arrays of atoms. So we can trap many atoms at the same time in 1D, 2D, or in fact, even 3D. And we can have a very accurate and precise control of the position of the qubit. And this is very interesting for the next, as we will see later. But as you can see on the top left, when we load the atom in the tweezer, you can see that sometimes there are atoms in the tweezer, so it's the orange dot that are here, and sometimes there is no atom in the tweezer. And this is because when we load the tweezers, there is a stochastically effect that leads to having one atom or zero atom in the tweezer because of collisions. The idea is very simple. Let's imagine that you have your tweezer that is on. An atom is coming from is coming close to the light, so is attracted, is trapped. But now let's imagine that you have a second atom that is coming. It will be also attracted by the light. So it will collide with the atom that is already trapped, so that at the end you have no atom in the trap. And this is quite annoying, in fact, because at the end what you want to do is to do some very accurate calculations. So you need the atom to be at very accurate position. So to overcome this difficulty, we will do what we call some deterministic preparation. So from a stochastically loaded array, we will produce a deterministic array of atoms with very precise position and so on. And for that, we use, again, a new trick, is that we will send a new light through what we call AODs, so acousto-optic deflector, that will be sent on the vacuum chamber. And this device, the idea of this device is very simple, is that you can change the position of a single beam of multiple beams so that you can generate what we call a moving tweezer. So you are able to generate now a light that you are able to move on your array. And the idea is very simple. At the end, you have a target array that is this one. And what you will do is that you will take the atoms that are not at the right position one by one, and you will put the moving tweezer on the trap, as represented here. You will increase the intensity of the moving tweezer so that you transfer the atom from the trap to the moving tweezer. And then if you move slowly enough your tweezer onto a second trap and you reduce back the intensity, you are able to move one atom from one trap to another one. So that from a stochastically array, you are able to produce a deterministic array. And this is more or less all the ingredients you need to prepare your register of qubits. And then you can play with it. So the basic cycle that I presented before can be summarized in this picture. So initially, you load the atom in the tweezer through magneto-optic trap, but we can forget about this. It's maybe a bit more to detail here. We have a stochastically loaded array. So we perform an image. We look at where the atoms are and where we want the atom to be. We perform all the move so that we move the atom at the right position. Then we prepare and cool the atom in the right state that I will describe after. And then we can start performing what we call the processing stage. So this means we perform a calculation with the atom. And this is what I will call during this presentation, the processing stage. And at the end, what you do is that you perform back a measurement so that you can see what happened on your dynamic of your system. And if you want to produce at the end the final wave function, you repeat this measurement a certain amount of time so that you are able to reconstruct carefully the wave function. Our machine works at a repetition rate of 1 Hertz. So it means that every second we perform a calculation. So this is basically the main challenge of our setup. So there are two main steps. Is that the first one, we need to be able, and the challenge is to achieve highly efficient register preparation. So we want a lot of atoms and atoms that are prepared in the right position. And then we want a very efficient and high quality quantum processing stage. So this means we want to perform operations after on the atoms that have quite a high fidelities. And this is basically how it works to perform calculation with atoms. So what I didn't mention is that, okay, just before I presented the fact that we are able to prepare an array of atoms But the point is that if you want to take benefit of doing quantum calculation, you need to be able to take advantage of the superposition and the entanglement phenomenon. And to do that, normally you need your qubit to interact. And the point is that atoms that are in the ground state, that are because we can trap atom in the ground state, and atoms that are a few micrometer in the ground state do not interact with each other. So this means that at the moment, we are not able to perform a very interesting calculation because we can do basically one qubit gate. But if you want to do something interesting, you need to entangle your state and so on. So and the trick that we use here is that we will use, in addition of the ground state, a Rydberg state. And the Rydberg state is nothing else as a highly excited state of your atom. So the idea is that you will bring your valence electron very far from the nuclei. And what you have generated, basically, doing that, is that you have your electron that is a negative charge. You have your nuclei minus the electron that is a positive charge. So you have generate what we call a dipole. And what is interesting here is that we know that two dipole moments can strongly interact via long-range dipole-dipole interactions. So the order of magnitude are between 1 megahertz to 1 gigahertz, which is also the order of magnitude that we are able to have in terms of driving Rabi frequency and so on. So this is the value that are very interesting to perform superposition and entanglement in our system. And one of the interesting effects that we use to generate entanglement is the following, is that here I have represented the energy level of our a two-atom system as a function of the distance. So here on the right, you have different states. So you have your two atoms in the ground state, that is here. You have one of the two atoms that is excited in the Rydberg state, and you have a final state that are the two atoms that are excited in the Rydberg state. So when you are at large distances, you don't have interactions. So if you send a beam that is resonant between grand to Rydberg, so this means that you excite only one of the two atoms. In principle, you are also resonant to excite the second atom. So in principle, you can do some Rabi oscillation between grand to Rydberg. But what is interesting is what is happening due to the interactions. So here you are still your ground state. And what is interesting is to look at what is the energy of your Rydberg state. As we say, two atoms in the Rydberg state have strong dipole moments, so they strongly interact. So what we generate is a strong interaction between the two atoms. So this strong interaction can be translated into an energy shift of this level. And the order of magnitude of this translation is C6, that is a coefficient, a van der Waals coefficient, divided by the interatomic distance to the power 6. And here what is interesting is if you have a light that is now resonant between grand Rydberg to Rydberg grand or grand Rydberg, you are no longer in resonance to excite into Rydberg. So you are not able to do Rabi oscillation between grand and Rydberg because this state is off resonance. So what is at the end the meaning of what will happen is that we will excite one of the two atoms in the Rydberg state, but we don't know which one. So we have a Rabi oscillation between grand and the superposed state that is Rydberg grand plus grand Rydberg. And this is the way that we generate superposition on our system. Very easy. So far, I explained you how we prepare the register, how we can generate superposition and entanglement, and basically I have presented two states that are useful for the calculation. So you have the ground state, that is a non-interacting state, and you have the Rydberg state, that is a strongly interacting state. Okay, but now let's imagine that we want to perform a calculation. So we have to decide where I encode my 0 and my 1 in my system. And in fact, if you think about that you have three main configurations. You can imagine that one of the ground state can be the 0, and your Rydberg state can be 1. You can imagine encoding the 0 and the 1 state into two different Rydberg states that can be also coupled. or you can imagine encode the information into 0 and 1 that are two different ground states of the atoms. And this is very interesting because depending on the choice of encoding, just this, you can perform analog or digital calculation. And this is what I will try to explain briefly here. So if you make the choice of encoding 0 in ground and 1 in Rydberg, what you have, in fact, is that it's very experimentally easy to implement because you just need one laser to excite 0 to 1. In fact, we do a two-level, two-photon transition, but this is very easy to implement. But this kind of system, you are quite limited by the lifetime of your atom. But the point is that if you look at the Hamiltonian that can be generating, encoding the information in these states, is that you can see that the Hamiltonian that you can reproduce is this one. So you have a first term that is proportional to sigma x with here the Rabi frequency, so the driving, basically the intensity of your laser or the square root of the intensity of your laser. You have a second term in sigma z, okay, nj, we cannot care, we can say that it's sigma z, that is proportional to the detuning of your laser, so how close you are from the two-photon transition. And then you have an interaction term that is represented here as a sum of all the interaction between all your pairs of atoms. And this is basically what we call an Ising model. And the point is that there are a bunch of applications, as I will show later, that will take benefit of that. A lot of problems, sorry, that can be mapped on this that can be mapped on this Hamiltonian. And this is why we use this encoding scheme when we want to perform analog calculation. On the other hand, you can encode the information in the two Rydberg states. So here it's a bit more complex to implement because you need to first, okay, when you will prepare your register, your atom will be in the ground state. So you need to transfer your atom in the Rydberg state and then to couple your two Rydberg states. So you need to add, in fact, microwave on your system. So it's a bit more complex to implement, but it's not impossible. And this is what has been done in Institut d'Optique in France by the group of Antoine Brouez and Thierry Lahaye. And basically, here, the Hamiltonian that you can reproduce is what we call a XY model that is very similar to the Ising one. So you have your term in sigma x and sigma z, and the main difference is connected to the interaction term, where you can see here that you have some cross term between sigma x and sigma y, so that you can generate what we call flip-flop experiments. And basically, you have a lot of quantum simulation and analog problem that can be mapped on this Hamiltonian. So most of the time, we will use this encoding when we want to perform analog calculation with the XY model. And finally, what is also interesting is that we can encode the information into the two ground states of the atom of rubidium. So we have hyperfine states, so we can choose different states as ground states. And we can take benefit that those states are ground states, so they have an infinite lifetime because they cannot decay in states that are even below, because they are the ground state by default. We can have and obtain very long coherence time, the order of between milliseconds to seconds. So it's very long coherence time compared to the analog side where the coherence time is around 5 microseconds. But the point is that indeed we will use this kind of calculation for digital calculation because you need an infinite lifetime and long coherence time. But on the other hand, we know that we will need to perform a bunch of gates, so we will be quite sensitive to noise errors. And the idea is that we can, in this configuration, perform some 1 qubit states very easily. The idea is that we want to transform 0 and 1 and 1 and 0. So there are two ways to do it. Either we couple those two states via microwave. So this is possible. This is something that is already done in the literature. Or we can couple these two states via what we call a two-photon Raman transition. This is what we do at Pascal, and this is very easy to perform pi state, pi rotation, or in fact, arbitrary single qubit rotation here. On the other hand, for 2 qubit gate, we need to generate entanglement, and basically we will play with the Rydberg state as an external tool to generate this entanglement, but it's not part of the encoding state, so it's just an external tool that we use to generate this entanglement. So I hope it was quite clear for the register preparation. Then we can choose different encoding as a function of the calculation that we want to do. And now I just want to go a bit deeper on the digital calculation because, as I said, we will be quite sensitive to physical errors in our system. So we need for quantum error correction in our system. So this is a bit what is represented in this slide. So at the moment, our current hardware quality, we have error rate per operation that are between 10 to the minus 2 to 10 to the minus 4. So each operation, we have a given error rate. And the point is that if you want to solve a calculation that is interesting for most of that is interesting, so this means with good results and valuable results, you need error rate that are of the order of 10 to the minus between 10 to the minus 10 to 10 to the minus 15. So we can see that there is a big gap between what is actually our current gate fidelity, basically, and what is expected to have good results. And the point is that we know that we can improve our hardware, improving, I don't know, the way that we control the fluctuation of the laser power, the laser phaseness, and so on. But we know already that we won't manage to reach this level of error rate. So we need to find a trick, and the trick is to perform quantum error correction, which is also what is used in classical computers. So we have also classical error correction protocols on your laptop. So the idea of this quantum error correction is very simple. So let's say that you have a first bit of information that is represented here by 001, 0000, and so on. And we have a communication channel. So this means that we will perform operation or just your qubits are waiting for other operation to happen. In fact, you have some error rate. So you have a probability to have an error at some point of one of the qubits. So for instance, this 0 that was here become a 1. So an error had happened. And the point is that this error can destroy totally at the end your calculation. And the idea is to do some quantum error correction. And the idea is very simple and it can be very illustrated in a pedagogical manner looking at the repetition code. And the idea is very easy that we will say, okay, let's encode redundantly the information over many bits. So let's take the example of 3 bits. So the idea is now that we will consider that one logical bit, so the 0 logical here, correspond to 3 physical qubits in 000. So this is a logical bit used for your calculation. Here it's the physical qubit. So here it's basically your atoms. And you will do the same for the logical qubit that is 1. It will be 111. And let's now look at what happened if an error happened during a calculation. So let's say that our initial bit that we are looking at is 0 logic, 0 logic, 1 logic, 0 logic. So in terms of physical qubit, this is what is represented here. So 30, 30, 31, 30. Let's say that again, an error is happening and you have 1 bit flip. So this atom, instead of being 0, become a 1. But the idea is that you have encoded redundantly the information just before, so you know that only those 2 states exist. Okay? So if you have one state that is something else, it means that an error happened. So if you look at the first bit 000, you know that it's a bit that exists, so it's 0 logical. So this is what at the end you obtained. Here you look at the second logical qubit, you have 0, 1, 0. So you know that this state doesn't exist. And if you have chosen the number of physical qubits properly, considering the error rate, you know that this state doesn't exist. So there is a high probability that this 1 should be corrected in 0. And you have some protocol after to change the 1 into 0 during your calculation. So in principle, you have detected an error, you can correct it. And for the rest, it's not affected. So at the end, what you did is that thanks to encoding redundantly this information, you were able to detect when there is an error, to correct the error, and at the end of the calculation, even if an error happened at the physical level, you obtain at the end the logical state that you have initially. So this is the principle of error correction that we implement in our quantum processor units. But compared to what I presented just before with a very simple view where I show you just an array of registers and then we just perform operation, the architecture to perform this kind of quantum error correction protocol is a bit different because we need to have the possibility to detect error and correct error during the calculation. So this means that the architecture we use is a bit more complex compared to what I mentioned so far. So basically, what we have is that we will have a storage zone where we can store all our atoms that are not used at a given time during a calculation. Basically, we know that sometimes we will perform some CZ gate between two patch of logical qubits, so the other qubit basically have to wait. And this is a bit what is represented here. So this is the atoms that are waiting for the other operation to happen. We have also an ancilla qubit reservoir. So this means that we have a bunch of atoms that will be used here to detect the error during the calculation and to correct the error during the calculation. And what is the strength of neutral atom is that we can have a hole-to-hole connectivity with very large flexibility. So basically, as we have the possibility to move the atoms before, during the sequence, and even after if you want, basically you can perform interaction, you can generate kind of hole-to-hole connectivity. So it's very easy to make this logical qubit composed of 25 physical qubits interacting with this one because you can just move the atom in an entangling zone where you will excite the atom in the Rydberg state, perform your CZ gate operation, and then you can bring them back in the logical qubit storage. And during the calculation, as I showed before, we need to have the possibility sometimes to check if an error happened. And for that, we have an extra zone that is here that is called the readout zone. And the idea is that sometimes we need to perform the measurement. So we will bring the atom in this lattice here. We can perform our measurement and then depending on the final result detected by our camera or by other things, we can decide if there is no error so that we can continue our calculation as before, or if we detected an error so that we start performing operation between our atom and the ancilla qubit reservoir. So what I want to say basically here is that our neutral atom technology is very suitable to perform at the same time analog calculation because it's very simple as I showed before because we don't need to move atom during the calculation, we don't need to do quantum error correction, but our architecture is quite good as well to perform digital calculation and fault-tolerant quantum computing. And this is a small video. I don't know if I will be able to run it. I will launch it. So this is more or less the typical kind of circuits that we run on our experiments. So here you have indeed the storage zone. Here you have the entangling zone. And here you have the readout zone. So this is an implementation that we did this year with a small amount of atom, but this is already quite an interesting proof of concept, where here you can see that indeed, if we want to run a circuit, we can really move the atom where we want, make interaction between very different atoms separated. So this is the strength of atom, and at the end, it's not so difficult, and the quality of the operation are quite high, and this is what I will present in the next. So here, just before I presented all the principal basically how we can perform calculation in our QPU. Now I want to explain a bit more what does it mean to build a quantum processor unit in a company. What are we doing at Pascal in terms of R&D, in terms of industrialization, sorry. And as we are a full stack company, we are also developing algorithms with clients, and I want to highlight a few use cases. So I will try to be short enough. So maybe I should have started with this slide initially. So Pascal is a French company founded by 5 co-founders with indeed Alain Aspect, who had the Nobel Prize in 2022. In 2019, by 5 co-founders, we are already almost 260 employees, maybe more so far. We we did 2 fundraising so far with 140 million in total. And as we will show, the size of a quantum processor unit is not that big. It's 2 meters per 3. So it's something that enter easily in a room. And as mentioned in the previous talk, we also work in a room temperature. So that's an important point as well. So as I mentioned before, so we are a full stack company. So this means that we develop application in collaboration with different clients. So we target a lot of application because, as I mentioned at the beginning, for analog calculation, it's something that has already value in the short term. So right now, where we can do calculations that are very close to what we could say be a quantum advantage, but the point is that maybe the practical relevance, we still have to work on it. And we work with a bunch of companies, so on optimization problem, on machine learning, on the chemistry, drug discovery, and so on. So I will highlight a few use cases after that. We also develop quantum software because, okay, people that are outside the company doesn't know so much how works a quantum processor based on neutral atoms. So we need to develop software that are easy to use if we want people to run themselves calculation through the cloud on our quantum processor unit. So we develop quite a lot of software so that it makes easier the life of people who want to develop on our quantum processor units. And we have a quantum hardware teams where we have a bunch of electronic mechanics and so on. So this is what I want to mention by a full stack company. So our main objective is to push R&D efforts to build industrial grade quantum processor units, to develop algorithms for new application, and to give access to our processor units or to install those processor units on-premise to different clients infrastructures. So I just want to highlight what is currently done at Pascal in terms of R&D efforts. So this is a picture of 2019. It's just to show you the difference between this setup that was the first QPU at Pascal, that was in fact at Institut d'Optique. So it's clearly an academic lab experiment. So it was our first setup that we used to solve some very basic use cases, but I think it's quite interesting the value that was shown in those papers where we managed already to do what we call graph machine learning, or we work with a bank on the financial risk management. So I recommend you to read those articles if you are not so expert in the analog calculation mode. And now this setup totally changed, so it doesn't look anymore to this, and is dedicated in 1 qubit and 2 qubit gate, and mainly on testing QEC, quantum error correction protocols, and is targeting fault-tolerant quantum computing. In terms of fidelities that we have, for the 1 qubit gate, we have a bit more than 99.9% of fidelity. For the 2 qubit gate, we have almost 98% of fidelity, which is not that bad. And obviously, this setup is still used for R&D purpose, so it's not something that is available for client calculation. So the idea of this setup is to push, quite similarly as an academic lab, some new things to try to be state of the art, basically. We have another setup that is called Humber, where the idea is to push the number of atoms that we are able to trap, so the number of qubits that we can play with. And this is a paper that we published, in fact, last year, where we were able to generate more than 2,000 traps. As I said, our array are stochastically loaded, so in fact, at the end, we have a bit more than 800 atoms. And this is a kind of picture that we obtained. So here it's the 2,000 traps that are on. So that's quite impressive. And this setup, the objective, there are two objectives on this setup: is to push the number of qubits that we are able to generate, and to de-risk what we call a cryogeny environment, where we put the vacuum chamber into a cryogeny setup. So it's a very small cryogeny setup. It's not something compared to other technologies. And the idea is to try to use this cryogeny setup so that we can obtain, in principle, longer lifetime of the atom in the tweezer. So in fact, we can keep atom in the tweezer for more than 1 hour. So this is the strength of the cryostat. It means that we can, in principle, do very long calculation in those kind of setups. Obviously, we are a bunch of other R&D setup, but I just wanted to highlight the fact that we push both the scalability in terms of number of qubits and the features that we are able to have with the 1 qubit and 2 qubit gate, as I shown before. Finally, I will try to be a bit more fast. Just to mention that we did a lot of effort into industrialize our setup. So we have already built the setup that is shown on the right. So as you can see, it's very different compared to the first machine that we had. So we have almost no optical table anymore, and everything is packed inside. So it's a machine that is already available through the cloud via different cloud infrastructure or via our internal cloud platform. What is the strength of this platform is almost everything is monitored and easy to maintain. So we have adopted a kind of modular approach. So if, for instance, something is broken in the QPU, we can clearly remove part of the QPU and replace it directly. So it's very easy to maintain and it's very fast. So this helps us to have a very to have our machine that are almost 24 hours on the cloud without stop. We launch a bunch of algorithms on it. So the specification of this QPU is 100 at the moment. I think we push it to almost 300, but it's not available yet through the cloud. It's just we are just testing few things from a R&D perspective. We have this year built three machines simultaneously that we delivered on-prem to different clients. So two in HPC Center at CEA in France and at Jülich in Germany. And we have delivered the first machine in a private clients, that is Aramco. So the specification of this machine are quite similar to the one I presented before, but we add some extra features with local addressing beams. And the specificity of this machine, sorry, I didn't mention it yet, is ready to perform analog calculations. So they are not yet adapted for cloud, for a digital approach. And finally, what I can say that maybe you can have a look to this picture. So we use already our quantum processor unit to solve some concrete problem in terms of quantum simulation, optimization problem, and graph machine learning. So we work, for instance, with Thales on the scheduling of satellites. We work with EDF in France for defining how we can optimize the position of electric power bank in the territory and so on. So I put some references. The slide is not updated, so don't hesitate to have a look to the literature with more recent developments, with more qubits. I think they are a bit more interesting, but it's just to highlight that in the analog mode, we can have already some short-term applications that are very interesting to look at. And finally, in addition to install on-prime calculator, we have also some quantum processor unit that we keep at home and that we give access through the cloud. And for this, we have a cloud platform, and we have developed an open source software where it's very easy to send the calculation on our quantum processor units. So if you have some idea of things that could be launched on the quantum processor, on our quantum processor unit, don't hesitate to contact us so that we can see what is possible to do and to see if it's possible to give you some cloud hours or to, yeah. So I give here some references about the repository of Pulsar. That is a software tool that we use to generate sequences or to launch calculation on our system. And if you want to have access to the cloud platform, don't hesitate to contact us and to contact me directly after the presentation. So it was, I think, the overall of what we do at Pascal. So we push the R&D, we push analog and digital calculation. We have quite high fidelities for our gate, but we are still pushing for them. We are starting to do quantum error correction protocols. So I think this is a bit aligned with all the different companies in the world. And voila. Thank you for your attention. I hope it was that it will be a bit more clear for you what means doing calculations with atoms.
Thanks a lot for the presentation. Dear participants, welcome here after the afternoon break or lunch break. I would like to apologize for skipping one talk, but Arun wrote us this morning that he has some injury-related problems, and he was not able to present his talk. Therefore, we continue with Elisa Baumer Marty. She's a research scientist at IBM in Zurich, where she currently explores different applications of dynamic circuits. She received a PhD in quantum information theory from ETH Zurich in 2022. So please, Elisa, the screen is yours.
Hi, thanks. Let me try to share. Sorry.
Yeah, we can see the screen and we can hear you.
So welcome everyone. Thanks a lot for the invite. Yeah, I'm happy to tell you in the next 40 minutes what dynamic circuits are good for, and especially how we can use them for efficient transpiling quantum computation. Just a very quick note in the beginning, because I guess my name may be a bit confusing. So my name used to be Elisa Baumer, and now I got recently married this summer. So now I'm officially Elisa Marty, but I'll just keep both names for now so people can make the connection. Anyway, to give you an outline, I'm first going to start talking a bit about the IBM quantum roadmap, also talking about then the road to fault tolerance. Then, of course, I'm talking about dynamic circuits, because that's has been my main area of research in the last years, and how we can use them to create long-range entanglement, and how we can use them for the quantum Fourier transform. And then talking about our latest result, which is showing how you can implement the approximate quantum Fourier transform on a line in logarithmic depth. So let's start with the key milestones that we at IBM see for bringing useful quantum computing to the world. So the first milestone was actually, we've reached it in 2023, where we've established quantum utility. Then for next year, so by the end of 2026, we want to reach quantum advantage. And then by 2029, we want to deliver the first large-scale fault-tolerant quantum computer. Now, I think there's been quite some confusion about the definition of quantum utility versus quantum advantage. And probably it also depends who you ask, but let me quickly go through what we understand by utility and advantage. So quantum utility, which we've reached 2023 with a utility paper, is the demonstration that a quantum computer can run quantum circuits that we cannot simulate classically anymore. So that we're far beyond the classical simulation regime, basically, and that we can execute them successfully. However, what it doesn't mean is that running these quantum circuits is actually the best way to solve some problem. So this, however, then is what we understand by quantum advantage, where we understand that we want to show that a quantum computer can solve a problem more accurately or cheaper or more efficiently than a classical computer alone. So the difference is really that, okay, with utility, we showed we can run quantum circuits that we cannot simulate anymore, but there may be other better classical methods for solving the same problem. And then quantum advantage means that this is actually the best way to solve it. And well, as I said, we expect quantum advantage. We hope to reach it by the end of next year with the help of the community. Now, there's two important points that we want to do when we have this kind of definition for quantum advantage. First of all, we need to make sure that we can somehow verify that our results are correct, because we're running them on noisy devices. So either we need some efficient classical verification, or some guaranteed solution bounds, or some provable confidence bounds. And then the second point is that we don't expect quantum advantage to come at one moment in time, and then we've reached it, and that we can make that claim. But the idea is more that we can make a hypothesis that we have reached quantum advantage, but then there may be a back and forth between quantum and classical algorithms. So then maybe the classical algorithms are going to improve a bit, and then based on that, the quantum computers improve a bit, and then it's back and forth until eventually quantum wins. But so it really is a hypothesis that we're making, and it's not going to be a sharp transition, but like more of a smoother transition into the quantum advantage. Now, here's the quantum roadmap. I'm sorry, it's not the very latest version, but it's like a few months old. So there's a few more green check marks actually by now. But I guess it's hard to read, so let me zoom in a bit. I hope that works. So basically what I want to focus on now, because I think that's what people mostly care about, is the hardware. So as you may know, in 2016, we started with the first 5-qubit system on the cloud. Then we increased the number of qubits to 27 and 127 in 22. And then eventually we noticed, though, that it's not just about the quantity of the qubits that you have, but you also should somehow evaluate the quality. And by that, so we started introducing these here, as you can see, 5K, which is the number of 2-qubit gates that we can run to still get some reasonable results. So last year we demonstrated that we could run 5K gates, 2-qubit gates on our devices. And now the goal is in the next few years to scale that up to 15K in 2028. Where then we would also, in addition to that, of course, also we want to increase the number of qubits, but not by making larger chips, but by actually combining different chips together. So that here, for example, if we combine 9 times 120 qubit chips, then we're going to have more than 1,000 qubits connected. And then importantly, by 2029, we want to introduce the first fault-tolerant quantum computer, which can run, hopefully, 100 million gates and has 200 logical qubits. And then in 2033, we want to introduce Blue Jay, which should run 1 billion gates and 2,000 logical qubits. Now, I know it's very ambitious to have these fault-tolerant devices on the map and running these many gates, and especially since we're also going to be using a different quantum error correction code, not the surface code, but the quantum LDPC codes, the so-called or specific one, the cross code. And so I want to show you a bit more, maybe some more details, showing you that we actually do have a planned path forward on reaching that goal. So first this year, and I believe it's been shown already, not, yeah, but so the goal is that for this year was that we demonstrate that we can do these 6-way connectivity, because as you know, the surface code only has 4. You have every qubit interacting with its 4 nearest neighbors. But now for the gross code, the one that we're considering, we have 4 nearest neighbors plus 2 long distance connections within the chip. So every qubit actually has 6 connections, and demonstrating this was the goal for this year. And then also showing that you can have these longer distance couplers. Then for next year, the goal is to basically show a full gross code. So connecting the device, one having also the really long range interacting gate, so that you can close the donut in that sense, or the torus, because it's, as you can see, it's yeah, we have to connect 2 ends of the chips and the other 2 ends as well, and then also to connect it to an LPU, so that we can process our data. And then by 2027, we want to show that we can actually connect 2 of these cross blocks. And then in 2028, we want to not only connect different cross blocks, but also connect them to a magic state factory. So with that, we're then able to do universal computation and also already connect maybe more than 2, but multiple blocks, which then sets the foundation to have our Starling device in 2029 with 200 logical qubits. And of course, magic state factories, so that we can do universal quantum computing. But yeah, coming back to the roadmap, of course, one thing that we definitely need to do error correction is we need to be able to detect our errors in real time and correct them. And to do so, one capability that we need to detect and correct these errors is so-called dynamic circuits, which you can see here. They were introduced in 2022. And now for the next few years, the goal is to scale them up further and further, because then we eventually need them for our error corrected devices. And this is, as I mentioned before, has been part of my research is on these dynamic circuits, though apart from error correction, they can also be used for different other things, like establishing long-range entanglement, which is what I'm going to show you now. By the way, I don't know how you want to handle questions. I'm okay if you interrupt me at any time, though that may be complicated, I guess, with people being with this hybrid setting of people being in the audience and online. Yeah, whatever. Otherwise, let's just have them at the end, maybe. So first of all, what are dynamic circuits? Dynamic circuits are some quantum circuits that incorporate a couple of different features, which are, first of all, mid-circuit measurements, which means that we can not only measure at the qubits or qubits at the very end, but at any time in between. Then classical calculations that are based on these measurement results of those mid-circuit measurements. And then feed-forward operations so that we can apply operations that are conditioned on our classical calculation, on our qubits, and apply these within the coherence time of our qubits, so within the quantum circuit. If we combine all these things together and incorporate them in a larger circuit, then this is what we call a dynamic circuit. But now you may wonder, why is this beneficial? Well, first of all, why do we need mid-circuit measurements? One example where mid-circuit measurements are already used, and you may not even know, but you may actually have been using them a lot, is for the conditional reset. So instead of waiting and cooling the qubit down, what you can do is you can measure it, and then based on the output, if the output is 0, you don't do anything. If you measure 1, you apply an X gate, which means in both cases you end up in the state 0, and that is the conditional reset. That is quicker than normally resetting qubits. And then, but okay, why do we need classical calculations? Well, you may wonder, classical calculations, are we supposed to use quantum computers because they're faster than classical computers? Well, for certain problems, of course, we expect that quantum computers can give an advantage, but this does not hold for all kinds of computations. Like in general, classical computations are much faster, have a higher fidelity, and have no connectivity constraints. So if I just wanted to add up two large numbers, I wouldn't use a quantum computer for that, but it's better if I use a classical computer for that. Which is also the reason why we have these hybrid classical quantum algorithms, like, for example, VQE. But in VQE, for example, the idea is that you run a quantum circuit, you measure all qubits at the end, and then based on the outputs, you apply the classical optimization algorithm, and then you start a new quantum circuit. Now, the goal here is that we're not doing first the quantum, then the classical, then the quantum, like successively, but that we incorporate it within our quantum circuit. And the most famous application that I've mentioned before already is error correction, where we want to directly detect our errors and correct them while we're running our circuit. But then, as I said, we can also use the classical calculations differently, which is, for example, as information transfer to spread correlations faster, which then allows us to create long-range entanglement in a shallow quantum circuit. But now you may wonder, why don't our measurements make the state collapse if we measure the qubits already halfway through the circuit? Let's consider an easy example. If we have 3 qubits, and let's say we put the first and last in superposition, and then we apply these CNOT gates in between, and now we measure the second qubit. Now the post-measurement state, you can do the calculation to see that, it's either 0, 0 plus 1, 1, or 0, 1 plus 1, 0. So one of the two Bell states is the output that we get, each of them with probability 1/2. However, this is not actually a Bell state now in the end, but we're getting a mixed state because we don't know which of the two states we're in. So if we now wanted to continue our computation, we had no clue what state we're actually in. But if we apply conditional gate, because here with this measurement, we know that if we measured 0, we're going to be in this state. If we measured 1, we're going to be in that state. So now if we apply a conditional gate that is conditioned on the output to be 1, we flip the second qubit. Then that means in the case where we measured 0, we're not doing anything, we're staying in this Bell state. Well, in the case where we measured 1, we flip the second qubit, which brings us also to the first Bell state. So in that case, then the final state would be that Bell state, and we have not a mixed state anymore, but a pure state. So we can use dynamic circuits to create entanglement between the first and last qubit without a direct link in constant depth. Of course, now with 3 qubits, it's not that obvious that it gives any advantage, but you can do that on more and more qubits, as you will see in a bit. And then the idea is very similar, but just scaling it up, which is especially useful for quantum devices that have a limited connectivity like ours. But now you may wonder, why do we need the feed forward here? Why couldn't we just apply it in post-processing? Well, the problem is that the post-processing works as long as we can simulate the different outputs to the end of the quantum circuit. Because if we wanted to apply an X gate here, but we're not actually applying it, then we would need to see how the state changes if we applied it only in post-processing. So we would need to be able to simulate our quantum circuit. And well, for these small circuits, of course, we could do it. But the idea is that in the end, we would like to run quantum circuits that we can't simulate anymore. So then we cannot do post-processing, but we need to apply these dynamic circuits and the feed-forward operations directly. But yeah, this was an example of not so long-range entanglements. So let's see how that works when we can actually have a longer distance, like really do long range. So we can implement long-range entangling gates. One reason I call them long-range is if we say that we have some local connectivity, and then I want to entangle 2 qubits that are distance n away. If I would do it just with unitaries, then the depth of my quantum circuit would scale linearly with n. Like we can see here the circuit. Let's say I want to do a C0 operation between the first and the last qubit, and there's like n qubits in total, and I only have linear connectivity. Then I would need to basically swap the qubit to the middle, apply the C0, and swap it back. Similarly, I can prepare long-range entangled states if I want to entangle n qubits. And then even if I had an all-to-all connectivity, then I would need then my depth would scale logarithmically with n. If I only have linear connectivity, it would actually scale also linearly with n. So this here, for example, is a GHZ state preparation, where I start by putting my middle qubit here in superposition and then spread the entanglement in both directions. However, if we now use dynamic circuits and the trick that I've just showed on the slide before, we can create long-range entanglement in a constant depth quantum circuit, which for the C0 gate looks very similar to what we've seen before. So we put every second, where we basically prepare a lot of Bell states in between and entangle them. So we have 2 layers of entangling operations. And then we measure all the qubits in the middle, half of them in the Z basis and half of them in the X basis, and apply operations that are corresponding on the sum of the different outputs, so X and Z. And this corresponds then to a C0 gate. And similarly for the GHZ state, we also have these 2 layers of entangling gates and then measurements on every second qubit. Then we apply these classically conditioned gates, the feed-forward operations. Then we have a GHZ state on every second qubit, and then we can just simply reset the qubits that we've measured and entangle them as well. So we have a GHZ state on qubits. And both of these operations have the same depth no matter how many qubits I add. So that's why it's constant depth. Now you may wonder, though, how that can be constant depth if entanglement cannot spread faster than an information light cone. And that is actually a fair point, because it's not truly constant depth in the sense that, yes, the quantum circuit is constant depth, but the classical operations are not. Because as you can see here, I need to add up like n or n over 2 different bits. And of course, adding up 20 bits takes longer than adding up 2 bits. But on the other hand, classically, adding up 20 bits doesn't take that long, hopefully. So the classical operations, since they are so much faster anyway, we consider this as constant, because compared to any of our quantum operations, it's almost constant. And our quantum circuit has a constant depth. Like there, the operations are always the same. It's really just this classical part where we need to do more operations. But yeah, so by using this classical calculation, we can thereby transfer the information fast. So we have experimentally tested that as well, of course. And you can see here, this was actually done 2 years ago, I think, or even 3, no, 2 years ago. So some systems were a bit older. I guess by now you could get much better results in both cases, but you can already see here that the dynamic circuits in the beginning, they were a bit worse because as you can see here, the circuit, it's not just depth 2, right? It has depth, whatever, 8 or something, depending on how you count, and you have the measurement and feed forward, which takes some time. So you have the offset that for small n, it's a bit worse than doing it the unitary way. But since it's constant depth, if you increase the number of qubits, you will be better than doing it in the unitary way. We saw that both for the CNOT gates and then for GHZ states, we expect the same. And now the outlook that we had on, and that we made at that point, was that we can use this gate teleportation as a workaround to reach an effective all-to-all connectivity by, for example, assuming that you divide your chip here, this was the heavy hex chip, into system qubits, which are the pink ones, and ancilla qubits, which are the blue ones, the light and dark blue ones. And then that's in a way that any qubit is connected with any other qubit. So you could basically have an effective all-to-all connectivity. So of course you cannot run too many gates in parallel. That's why you could also sacrifice some more system qubits to have more parallelism allowed. But yeah, it's effective. It's not real all-to-all connectivity. But still, we could see that dynamic circuits are very promising to help us overcome the current limitations that we have on hardware, especially as we increase the number of qubits. But okay, then that was 2 years ago. And then last year, we actually came up with some more constructions for using dynamic circuits, but in a setting where we just considered a 1D line. So really the minimal connectivity that you need. So we considered having n+1 system qubits that were alternating with n ancilla qubits. And then looked for different quantum subroutines that we construct in constant depth with dynamic circuits. So an easy example is the CNOT ladder. It's basically also what's needed for the GHZ state prep. But essentially we can, if we have n CNOT gates, we can implement them with this quantum circuit in constant depth. Then in a similar way, but a bit more elaborate, you can create a circuit for the fan-out gate. The fan-out gate means that you have n CNOT gates that are all conditioned on the same qubit, but acting on different qubits. And that as well you can implement in constant depth. And then the last thing was the CNOT gate, the long-range CNOT gate again, similarly to before, but the difference now is that we only have this 1D connectivity, and every second qubit is a system qubit. That's why we need a few more qubits than before, because we essentially need to jump over the CNOT gates, jump with our 4 CNOT gates over the system qubits that we don't want to change, because we want to keep them. They're used for the algorithm or something. But the big advantage is that the example we considered before, here we only had maybe 30 system qubits, while now every second qubit would be a system qubit. So we could use way more qubits in that way than the way we considered before. And then basically these constructions I just showed, you could also combine them a bit further to get multi-qubit parametrized rotation gates, like a multi-qubit RZZ rotation. Like having all these RZZ gates could be done with 2 CNOT ladders and RZ gates in between, which again, we can do in constant depth. We could do parallel RZZ rotations and then even parallel generalized fan-out gates. So having controlled unitaries that are all arbitrary single qubit unitaries, but controlled on the same qubit. We've also experimentally tested that, and there we saw as well as before that the measurement-based protocol has a much better fidelity than the unitary, as we would expect. Especially, I mean, after we reach this crossover point, which is at maybe 8 qubits or something, similar to the results I showed before. So that was for these subroutines. But now I told you that my main project was actually on the quantum Fourier transform, or my latest project, let's say it that way. But before I get into the more general QFT with dynamic circuits, I want to show this other result from last year. But first of all, why is the quantum Fourier transform important? Well, it's needed for a lot of quantum algorithms like Shor's algorithm or quantum phase estimation. And in these algorithms, it's often followed by a measurement in the end. So the unitary circuit would look like that for the quantum Fourier transform. And then if we have measurements at the end, we can use the principle of deferred measurement and move these measurements basically through our controlled gates here. These are controlled phase gates, which are symmetric, so we can also turn them around, and then have classically controlled rotations. So instead of having of the order of n squared 2-qubit gates that we would have here in the unitary circuit, we would now only require n mid-circuit measurements and then just classically conditioned gates, which do not require any connectivity. So we wouldn't have these connectivity constraints anymore that we have here, which of course makes it much easier to implement. And we've tried it out. You can see here the dynamic circuits and the unitary circuits, the fidelity for increasing number of n when implementing the quantum Fourier transform with measurements, with and without dynamical decoupling. But again, that was done more than a year ago. So that was on the older devices, which had more crosstalk. So by now we would also expect that results are better. But that's also why you can see such a big difference when you use dynamical decoupling. But okay, so the two dynamical decoupling curves are the better ones. And you can see with unitary circuits, we managed to get like visible fidelities up to maybe 11 or something, while with dynamic circuits, we could go almost to 40. However, of course, this fidelity looks not that nice, right? Like even here at 30 qubits, the fidelity is maybe 10%, which looks very little. And then especially if you compare it with other people reporting different fidelities, we noticed that other people reported, for example, 100% at 27 qubits, which we digged into, which is not the fidelity, but they basically apply a majority vote at the end of your circuit. Like you run the circuit with whatever 1,000, 10,000 shots, and then you do a majority vote and just take as output the bit string that got the most votes, which you can do, but only if you promise that you only have one output string. If you have different output strings, then it doesn't work. But if you promise to have one output string, you can apply this technique. So we've applied that as well, and we noticed that with that we could actually go to like 38 qubits and still get 100%. We call it now, of course, not fidelity because it is not the fidelity, but average result success probability, which was pretty nice to see that even with this kind of small actual process fidelity, you can still get these big numbers then, like get the correct bit string if you have one. And just maybe to visualize it a bit more, because when you talk about Q of t, people usually think about periodic functions because that's what it's mostly applied to. So we just wanted to have an example on a periodic function. So we prepared a periodic state here. This is the state before we apply the Q of t, and then we applied the Q of t. In blue, you can see how it ideally is supposed to look like. In pink, you can see the dynamic circuit results, and in light blue, the unitary ones. And as you can see, the dynamic circuits quite nicely resemble the ideal case, while the unitaries are pretty flat. Well, you can still identify the peaks, I guess, but not that well. And this was only done on 10 qubits. But okay, as you may have noticed, this now was not the general Q of t, because the protocol I just described only works if you measure your qubits, all of your qubits, after applying the Q of t, which is the case in like the end of Shor's algorithm, the end of like at phase estimation, and so on. But of course, you also often want to implement the quantum Fourier transform somewhere in the middle of your quantum circuit. For example, if you have arithmetic operations that you do that are often performed in the Fourier basis, then you cannot measure qubits after the Q of t. So then the scheme before doesn't work. And basically, the latest paper that we put on the archive like half a year ago shows, and there we derived that you can approximate the quantum Fourier transform with an error epsilon in a depth that scales logarithmically with n, while using only of the order of n qubits on a line. And before it was known that you can do the approximate Q of t in logarithmic depth, but only using all-to-all connectivity. And well, all-to-all connectivity is unfortunately not what we have on our devices, so this makes it substantially more feasible. Now, the way that this construction works, it's similar to some older work, like from 25 years ago, where all-to-all connectivity was assumed though. But the construction requires basically two different operations. One is called the QFS, the quantum Fourier state computation, here the blue one. And basically there we have what it in general does is it starts with two registers, one register that has a computational number J, like in the computational basis, and then phi of B, with the phi we refer to the Fourier basis. So some number B encoded in the Fourier basis. So you can think of it as having a state B and then the QFT applied on that. And now the QFS operation adds the number J, the first register, into the Fourier register, so that we have then phi of B plus J. And then the second operation has, again, some state B in the computational basis and phi of J in the Fourier basis. And then this time it does kind of the opposite thing. It adds the number that is encoded in the Fourier basis onto your bit string. However, it's not an addition in the normal sense of bit strings, but it's binary addition. So you really just add up like each pair of numbers modulo 2. But now how we can put that together is, well, the initial state can be any computational. Of course, that all works in superposition as well because it's linear. But let's just assume we have a bit string J and then some ancillary register 0. Now we apply Hadamard gates, and Hadamard gates applied to 0 bring us to the equal superposition. And the equal superposition state is actually our Fourier state 0. Now, if we apply the QFS, we add J into the Fourier basis, so we get J and phi of J. Then we apply the Fourier phase estimation, where we add the J onto our state J. And since it's binary addition, J plus J equals 0 then. So we have 0 and phi of J, and then we just swap it so that our final register is again we have in the second register our ancillary state 0 back. And now we went from J to phi of J, so this would implement the QFT. However, well, if we wanted to implement it exactly, the QFS would require of the order of n squared gates, because you would need, these are all controlled phase gates, and you would need controlled phase gates between every qubit of the first register with every qubit of the second register. And maybe you can't, I'm not sure if you can see it. These are different numbers, and the numbers refer to the rotations. A smaller number, it means a bigger angle. A larger number means a smaller angle, because the angle goes with 1 over 2 to the k. So the exact QFS would give us the state. But now what we can do is it's similar to the typical approximate QFT. We can define some value k max, and then we say that every angle that whenever k is larger than k max, so the angle here becomes very small, then we omit these rotations. So all these rotations between qubits that are far away are essentially omitted, but these are also all rotations by a very small angle as it scales with 1 over 2 to the k here. So, and the k scales logarithmically with n. And then if we do this approximation, we can see that we can just implement it by doing nearest neighbor operations and n layers of swaps. Sorry, not n, k max layers of swaps, so logarithmically many layers here. And then we just need to do nearest neighbor rotations, no controlled phase gates, and then we swap back, and then we have essentially implemented the QFS in logarithmic depth. So our result was basically this part was kind of known. We did show it in a bit more detail though, because what you have to be careful is that you can now not only consider the gate fidelity of this gate and the approximate and the real gate, but actually you need to consider that your states could also be entangled with some environment. So I think it's much better if you, so we here consider arbitrary states with an environment that can be how entangled. So this is the diamond norm. For those of you who had some QIT classes, you probably have heard of that. So yeah, what we showed is that if you have a state that is arbitrarily entangled, but has some, can have any state here. This gives us an error epsilon when we consider a depth that scales logarithmically with n over epsilon. And then the second implementation, the second operations is the Fourier phase estimation. And here we have the exact Fourier estimation that I described before. That would be adding b on j. And now the approximation works in a way that we estimate all of the j that we want to add. We essentially estimate it with small but exact QFTs. So you can see here we have QFTs acting on 2k, where k again goes logarithmically with n in qubits. So they have a depth of logarithmically in n of k. And then this approximates the state j, the one that we want to add on b. But the trick that we do is instead of getting exactly j, we will get kind of a smeared version of j. But now we don't add all bits, but we only add the most significant k bits, and the other k bits we leave as room for some errors because it's a smeared distribution. So this guarantees that with a very high probability we will get the correct state. And then we do it again for the other k, those that we didn't do before, so that in the end we have added all of our bits onto the b. And then again we showed that this you can approximate it with an error epsilon. However, now there's a big issue with it, which is that it doesn't work for all input states. It works for most input states, but whenever you're very close to the bit string all 0 or all 1, which is close together, then if you have a smeared distribution around that state, the most significant bits may also change. So for those few, it doesn't work, which is why we constructed something that makes it almost uniform. If we have almost uniform inputs, so they don't have to be exactly uniform, but more or less uniform, then it works, because then on average, we only have this epsilon error, which is fine. But yeah, for that, we need to construct, if we generally want it to work, we need to construct uniform inputs, which you can do with a quantum adder, which adds our bit string C to our bit string B. If we have 2 qubit registers, it adds them up, but this time that's normal addition, not the modulo 2 binary addition that we had before. And now we choose 2 random numbers that we can classically choose, and we basically add one of them in the phase and one in the bit string. Then we apply our uniform QFT, the one that I described before. But given that we have these 2 random numbers, we have essentially the same as if we would take a superposition, because we have a uniform distribution in that sense. And so this guarantees that up to an error epsilon, this works. And then in the end, we kind of reduce it again, like we remove the C2 and the C1 again, so that we're back to our initial states. So that way we kind of first randomize our input and then unrandomize it by having our numbers C1 and C2 and subtract them again. And in the end, this still works of the order of n qubits, but it now requires an adder, which is something else. It's kind of a sub-result that we had, is that we constructed an adder that works on a line of qubits in logarithmic depth, because that is now needed. And this is where we require dynamic circuits, because so far we actually didn't require dynamic circuits. But to get this uniform input, we need this quantum adder. And it's actually quite simple if you consider the results we got before, because that is a typical adder that was like this one is from Draper et al. It's called the Logarithmic-Depth quantum carry look-ahead adder. And it works in logarithmic depth, but it seems to require all-to-all connectivity, because it has these long-range entangling gates here, like from here to here, for example. But what we can see is that in each of the time steps, so anytime that I look, for example, this here and here, we have long-range entangling gates, but they're not overlapping. So with the construction we made before, we can apply them all in parallel by just having some ancillar qubits in between. So we can still implement the whole adder in logarithmic depth on a 1D line. It requires some extra qubits though, but then we can reduce them because we have classical inputs. Sorry, that was not very technical, but since I had quite some time, I thought I'm going to go into the details, especially since I was asked about this paper in particular. So now just very quickly, some more technical notes on how you can improve the implementation, and then that's it. So, well, I just showed you before that if we have uniform inputs, then we can apply our QFT on a line with 2n qubits, nearest neighbor connectivity, and logarithmic depth, which is guaranteed to work if our inputs are uniform, but it also works for most random input states because you're very unlikely to get a state that for which it doesn't work, that is very close to like all zeros or all ones. So it's not guaranteed to work for any input state, but for most states it works. So as soon as you can have some way to verify if your result is correct, like let's say in Schwar's algorithm or something, you get something and you can check if it works, then you may always take as first try this simpler QFT. That can be very relevant in practice. However, if you cannot verify your result and you want to make sure that you have up to an error epsilon implemented the QFT, then you want to do the construction with your uniform inputs. Yeah, and then that requires 4n qubits, so instead of 2n, but still goes logarithmic. And the depth goes logarithmic, but it requires some more operations. The prefactors will also be larger. Now you can still improve it a bit further by using the principle of deferred measurement, so that you basically your latest operations are not actually implemented, but you measure your qubits, the ancilla qubits that you need. You can measure them earlier and then apply classically conditioned gates for those. And you can actually also make it a bit easier if you run it backwards. So I now showed you the more intuitive way of first doing the QFS and then the FPE, but you can also swap it and just change the phase gates by a minus sign, basically. And then you can, the QFS then simplifies a lot if you use the principle of deferred measurement, so that there's more details in the paper. But if you wanted to actually implement it, you would probably do it the other way around. And there's also the chance that if you approximate the QFTs that you have in the FP, the small ones, if you again approximate them in the way that we did now for the big QFT, then you could potentially go to depth log n even, which would be nice. It would be another improvement to have an even smaller depth. However, one would need to carefully analyze the errors and check the trade-offs because you would need more qubits, and the prefactors would also increase a lot. So I'm not sure if it's like this, at which end it would actually be reasonable and make sense. We have not analyzed that. So lots of theory in the end. Sorry for that, but a bit more easier stuff in the beginning. So I hope that I managed to show you that dynamic circuits are very helpful, as they can help us overcome our connectivity constraints and reduce the depth, and thereby drastically improve the compilation of quantum algorithms. As we have seen, they are more and more important as we scale up the number of qubits. And we have already now seen quite some benefits of using dynamic circuits for optimizing the compilation of some quantum algorithms, but I believe there's many more applications that we can explore. And this has actually two different things. One is, of course, to overcome the current limitations that we have on hardware. But what I also think is quite important to consider is how to optimize the resources that are then required in the fault-tolerant compilation. Because in general, I think that's something that people should care about more and more now, because it's not that far in the future anymore that we're going to have fault-tolerant devices. So considering the resources required there, and then also how dynamic circuits can help, I think is also an interesting direction to go. And with that, I'd like to thank you for your attention.
Now, so I would like to thank you, Elisa, again for the talk. Dear participants, welcome back after a very short break. I would like to introduce our last speaker, Łukasz Pawela, who is Associate Professor at the Institute of Theoretical and Applied Informatics, Polish Academy. And yeah, I think I will give him the space to say us something interesting.
Yeah. So hello. I hope you can hear me. Yeah, I represent the Institute of Theoretical and Applied Informatics of the Polish Academy of Sciences when we work on quantum computing, and also a Polish startup Quantum.io, where we work on classical but quantum-inspired optimization solvers. And this allows us to converge on this nice area of testing the gaps on quite recent quantum advantage or supremacy claims. And we'll go through some annealing claims, Oracle algorithms that were implemented on the IBM machines, and some hybrid classical quantum optimizations also. Is everything okay? Yeah, okay, because okay, so we'll go through some motivation, then introduce the actual framework we are using, 3 case studies, some general lessons from our results, and a short summary how to proceed. Okay, so motivations and the definitions. So recently there have been a lot of papers coming out claiming some kind of quantum supremacy advantage, that it can outperform classical computations. I think the most well-known is all the stuff related to Google random circuit sampling, and then back and forth with various classical computing groups. And I think the latest result is that, well, you can beat the results and you can get the results in a reasonable time, but you need a full Chinese supercomputer to do that. So let's say that there's potential for some advantage there. But if you look at the claims, we have some 2 worlds. The first one is complexity theoretic speed up. So we have something like Simon's algorithm, which I will talk about, or Shor's algorithm, where we have some theoretical results that tell us that there is potential for quantum speed up. And there are experimental claims on NISQ hardware saying, like, for example, this device solved some problem faster, or that the solving of this problem on this device scales better than some classical algorithm. And we are in the NISQ era, meaning we have relatively small, noisy devices with strong hardware constraints, like the topology of the hardware, available coherence, available operations, and things like that. So the central question is, do these claims actually hold if you think about your classical baselines, how to implement them, and actually try to implement them with at least some efficiency in mind? And why we focus on runtimes and maybe some other metrics I'll introduce later, because in practice, what we usually can care about is how long we can get a solution that is of quality some epsilon. Maybe we are testing something and we know what's the optimal solution, and we want to test how close the device can get to that solution, and how much computing time, or maybe energy, because this can translate directly into energy. How much energy does that require? And for example, we can have that some actual separation can appear only for very large problems, which current devices cannot run. And for example, the IBM machine has 127 qubits. D-Wave's anywhere have around 5,000 or 7,000 now, but D-Wave Anywheres has other things going, so let's not focus on the number there. And everything operates on different timescales. For example, if you think of the D-Wave's annular, the annealing time can go from a fraction microsecond to a microseconds, and the clocks on a classical computer are faster, but every operation uses a lot more clock cycles, and we can see how that adds up. And what we arrive at is something that I call runtime-based supremacy. So for a clearly specified family of problems and quality target, the best-known quantum implementation should achieve a shorter end-to-end runtime than a classical method. Okay. And for optimization problems, actually, we have this time to epsilon metric, which is defined as displayed here. TF is the runtime, and the probability is the probability of being epsilon close to the best known or the optimal solution, if you know it. And you can think of this time to epsilon as the more or less an expected time to obtain a good enough solution with 99% confidence. And how you actually measure it is that you estimate this probability empirically, meaning that you have an ensemble of the same type of problems with maybe various optimal values, but the same, for example, topology. You run it, test it, how fast you approach the optimal value, and that's how you estimate the probability and just calculate this quantity. The problem is that the runtime is here, and the question is, what is the runtime actually on a quantum device? How you should calculate it? On the classical side, we have it easy. We implement some classical algorithm. Usually there will be some main algorithm loop on the CPU, GPU. Maybe if we go a bit further, we have FPGAs and things like that. And the overheads are usually well defined because we have some data loading, transfer between hosts and devices, stuff like that, but that can be reasonably measured and handled. And for a vast majority of problems, we have that total time is more or less equal to compute time, and some small, usually weakly dependent on the problem size constant that is related to the transfer, especially if we focus on problem sizes that current quantum architectures can handle. Then this overhead is almost negligible. On the quantum side, we have a lot of other things. We have on the quantum, if we think about quantum anywheres, we have the problem of embedding the problem on the graph, on the anywhere. Then we have the actual annealing time, which is also dependent on the user set parameter, because the annealing time is a parameter that is defined by the user. But we also have readout time of the results from the anywhere, thermalization reset. That's also something you have to think about when dealing with lots of shots. And maybe, and the question is, should you count something like cloud access, overheads, and queuing? Because reasonably, not a lot of people can access these machines, and to access some classical algorithm and run it locally is relatively easy compared to this. And of course, the same will go to the based gate computers. We have the transpilation of the entire circuit, depending on how complicated it is. It can take more or less time, but this still adds up, especially for small problems that are relatively easy to handle. Of course, we have the number of desired shots, we have gate times, and also readout and qubit reset. This all needs to be taken into account. And here's one of the main pitfalls that people fall into, that many supremacy papers count only some nicest looking part. For example, focus only on the annealing time for the Dewey machine and ignore everything else. And how the quantum annealer is constructed now, this is actually not measurable. This is a user set parameter, and we can believe it that it actually happened like this, but we don't know. In principle, as a user, we don't have access. Maybe if we have an engineering access to the machine, it's a different story. But as a user, as a typical user, we just don't know. And how we approach this problem? So we have this nice solver that is quantum inspired, and it's called the simulated bifurcation machine. And it comes from Hamiltonian dynamics on networks of nonlinear Kerr oscillators. And instead of some thermal noise, like, you know, the algorithms like simulated annealing, parallel tempering, stuff like that, you have some just in the algorithm, we will just call some random sampling function that gives you pseudo-random numbers. Here, the algorithm itself is deterministic, fully deterministic, but chaotic, meaning different initial states give you vastly different results in the computation loop. And the algorithm can be massively parallel, meaning we can very easily, and actually it's embarrassingly parallelizable, so we can have many initial trajectories simulated in parallel, and this allows us to explore the landscape of possible solutions very, very rapidly. And this algorithm is defined for the Ising problem that is the which we think of like this. So we try to minimize some energy, find such a configuration of SIs, which are just plus minus ones classical spin variables that minimizes this quantity. And how do we get this solver? I'm not going to go through the full quantum derivation and their simplification. I will start at the end, so at the final simplified version. So we start from a network of kernel linear oscillators. They are parametrically driven by P, and they are coupled, and that the couplings actually implement the Ising cost function. And under some approximations, we can actually arrive at this nice looking system of ordinary differential equations. And it turns out that this system can be solved very easily using just the symplectic Euler method. So it's also very simple to solve. So we just iterate this using the symplectic Euler method, and it's very nice. And we see here that we have a few hyperparameters here. The hyperparameter delta, xi0, and p of t. And you would think that we need a lot of hyperparameter tuning to get a good result, but actually, okay, so I have this here. So, but actually, if we think about it, then the coupling. Did I press? Oh, no, I didn't. Okay, the couplings can be chosen very easily as based on the Jij values. I will show the equation later, and the delta for vast majority of problems can be set to equal to 1, and P of t just ramps up from 0 to 2 linearly. And that's a very good first guess for a vast majority of problems, and this gives very nice results. And actually, there's not one simulated bifurcation machine. There are at least 4 known in the literature. The first one is the adiabatic simulated bifurcation machine, and that one is more complicated because it's a more complicated system of differential equations, and there's more terms there, but it doesn't give good results. Then we have the ballistic simulated bifurcation, which is schematically shown here how the states evolve for some very simple two spin system. And then you have the discrete and ternary simulated bifurcation. And where these names come from is this function here, this function f of x that is here. And this gives you various behaviors, and turns out that this function reasonably can be either identity, which gives you the ballistic simulated bifurcation machine. It can be the sine function, which gives you the discrete, or it can be a bit more complicated, which I will show later and discuss later, because that is what we actually use, and that will be called the ternary simulated bifurcation machine. And actually, you can think of this x's as positions of some generalized particle and y as its momenta. That's why it's labeled here as such. And this is for just 2 spins. If we go to a more complicated system, we can see that it evolves quite nicely, quite quickly, using these tricks with discretization and ternarization. And now the moment of truth, actually. Yeah, it works. Very nice. Yeah, so the animation, I don't know why it has such low frame rate, but still, this is how x1 and x2 evolve on this plane, given various bifurcation machines. And yeah, as this is a ferromagnetic system, they all go to 1 at some point. As you can see, that discrete and ternary work well, and the intuition behind this is that they are able to quite quickly explore quite a large region of the possible configurations. Because during the simulation, all this, I notice I put x instead of s there, because they are all relaxed variables, meaning they are from -1 to 1. And at the end, when we finish the entire simulation, we just take the sine function, and we say that this is our solution, this is our desired state. And yeah, how to make this stable? How to make this behavior stable? First of all, we have inelastic walls for the positions of the particles at 1 or at square root of 2 for some reasons. And if our particle tries to escape, because in principle we use the symplectic Euler method, and if we didn't introduce any walls, sooner or later the particle will escape to infinity because the system is unstable. So we introduce inelastic walls like so. So basically the momentum is set to 0 when the particle hits a wall, and it's restricted to that wall, and this keeps it nice and convergent. And the ternary discretization is just some fancy version of taking the sine function, basically meaning that only some of the spins initially are present in that term, and the rest are set to 0. Sorry, this should be p, not delta, of course, here. I don't know why I put delta there. So early in the run, many of the variables will satisfy the first condition, so they will be set to 0. So only the largest one, let's say, will have any dynamical behavior. And later, as p of t increases, more and more we join the computation, but all the others that started earlier should be already locked to something, should already be stuck at the wall. Again, and more, as I said, more variables join. And at the end, we take, as I said, the sign of the positions and say that this is our result. And yeah.
Can I have a quick question with regards to previous slide?
Okay.
How do you choose the p of t function?
It's I mentioned it. It's linear. It ramps up from 0 to 2 linearly.
Okay, just linear function.
Just linear.
Okay, has it got some big impact? Have you tried some different functions or?
Well, yeah. Well, it will have a big impact because it's a bifurcation machine. So I didn't go into details here, but the states for particular values of p exhibit a bifurcation. And if you ramp up it too slowly, the bifurcation will be at the very end of the simulation, and you will not get a good exploration of the entire parameter space. But you can also not ramp it up too quickly, and it turns out linear is fine.
Okay, thanks.
And of course, you can write this out as an algorithm. So we have an Ising instance, and we have some additional hyperparameters. So I said the symplectic Euler method. So we need some time step, the number of time steps, and the number of repetitions. So actually, the number of initial trajectories we simulate in parallel. And based on this, we can perform our simulation. As I said, the good initial guesses for the hyperparameters are as shown here. And then for each replica, you can run this parallelly on this GPU, for example, the entire algorithm like this. And we get NR total states from which we choose the one with the best energy. And that's the entire algorithm. The hyperparameter delta t here is interesting, but you also can just set it to some nice value between half and 1, and it's usually good enough. And then we can compute the metric time to epsilon and run it for an entire ensemble of solvers. And the question is what counts as runtime here versus what counts as runtime in everywhere else. So for this simulated bifurcation machine, we have the time on the GPU and the time of the overhead, which, to put things fair, we didn't count loading the instance from the disk and stuff like that, because for the quantum part, you also have to do it. And we assume that you have it in system memory available, so actually the only overhead is the transfer from the host to the computing device, so to the GPU, and then transfer back of the results. And for the wave, we have readouts which can dominate the annealing time. And I will show that later. And probably if you don't have instances that fit nicely into that graph, you would have some embedding. And for a given instance structure, of course, you can do the embedding only once and reuse that embedded graph. But still, you have to assign some fraction of the embedding time to each of your runs and think about that to make it more fair. So, case study 1, Ising Kubo on D-wave annealers, and this is where we discuss with this paper here, published in Physical Review Letters quite recently by Munoz, Bauza, and Lider. And they did some approximate Ising optimization on D-wave advantage with some special coding, with some special instances. I won't go to the details here, but these were the sizes of the instances they got. So from a few hundred to less than 1,500 spin variables. And they, as the figure of merit, they choose time to epsilon with relatively loose epsilons because they were around 1%. I think they were from 0.75% to 125 or 1.5, something like that. And they tested a range of annealing times between a half to 27 microseconds, and they obtained some results, but they compared it against some classical baselines, so PTICM, so it's parallel tempering with isoenergetic cluster moves, so it's a normal parallel tempering iteration followed by some special moves. I won't go into detail here. You can find it out easily how this algorithm works. And they argued that their D-wave implementation of decoding on this set of instances showed better scaling on the device compared to PTICM. And that was the claim of the paper. Okay, so what we did, we repeat the experiments on the same instances and we try to account for everything as they did in the first approach. So giving them being as most favorable to them as possible. And we run the simulated bifurcation machine on GPUs, on H100 GPUs, up to 4 of them. I think we used, and the measurements of times was as I mentioned earlier. And okay, good. And actually, these are the updated results. So, as you can see here in the gray region, it's set time because, as I mentioned, that they use annealing time as a proxy for the entire runtime, and that's not measurable in the device. So that's why we said it's set time, and ours is actually measurable, and we just fit a power law to this time to epsilon, and as you can see, depending on what time we count and how we count it, we get, first of all, on the implementation and how we run the PTICM, we got better scaling still compared to them. And secondly, the simulated bifurcation machine, especially if we go on the GPU times, outscales everything here very easily. And the problem is the instance size here, and we'll go into details about that because you can see that it's hard to tell that the algorithm really scales that well if you have relatively small instance sizes. Because if you have an exponential function and look at a small enough fraction, it's always linear. Or you can fit a polynomial, some polynomial always there, and it will still look very good. And here I presented the number of repetitions and the number of steps of the algorithm that was used to obtain the result for each of the sizes. And the nice part is that if you look at the D-wave results, then the higher the error, the better the scaling gets. So that's a nice observation. Whereas R stays more or less the same. For the smaller, it gets a bit worse. Actually, they perform some more experiments going to even smaller errors, and as expected, it tends to an exponential function if we get to a small enough errors. And yeah, And this is just the same thing, but providing the scaling exponent, we got the range of scaling exponents we got for various solvers and various epsilons. And as you can see, if we account for the time properly, and then we can have a classical solver that outperforms that what was presented there. And to show some more results, actually, yes, we went to some smaller errors, and then what we did was we, as I mentioned, we considered the entire runtime, so considering the readout times, not using the annealing time as a proxy for the runtime. And these numbers that were used to gain these scalings, you get actually as a report from your computation in the wave machine. So this is measurable, and this is what you can observe. So the scaling looks good, but it's because it's almost constant. And that's the takeaway here. If you look at these curves here, there's actually not much of a curve. So you see the errors are bigger than the than the value of the scaling, and that's because the readouts and all the other overheads dominate, and that's why you get constant scaling. And as you see, the raw numbers are also a few orders of magnitude bigger. Okay, and this is some more detailed plots, and as I said, how we try to fit some alphas for small errors, even very small, and yeah, this doesn't look so good for the classical solvers as we would expect for this larger alphas, but this is how they behave as a function of epsilon for the various solvers. And you can see that the behavior is quite stable for a quite wide range of errors for the SBM. So we have two gaps that we learn from this. The scaling advantage from pi to epsilon versus the number of variables. Using something unmeasurable, yeah, may lead to some advantage, but you need to consider full time, and the advantage might not remain. This of course can be fixed in the next generation of quantum computing architectures, and you point that out. And you really need to focus on your classical baselines. And I would argue ours is not still the best possible. There could be better ones. For example, if you use things like FPGAs and you design, or ASICs with designed circuitry for this problem or for using this solver, and you can argue it's a bit fair because quantum devices are also highly specialized, then you can get even better, not to mention the energy requirements. If you're focus on that. The other thing I mentioned, now we go into more detail, is the finite sizes of the problems. So the largest problem we studied was less than 1,500 variables, so not that large. And actually, with the SBM, we can go to a quite larger problems. We can easily go to tens of thousands. 100K is fine. The largest I was able to run was 450K, fully connected. So fully connected to, that's important. And the only limitation was actually the 1 terabyte of system memory I had. So yeah, of course it takes quite longer, but still. The takeaway, I think, is that we cannot make any scaling predictions and scaling claims based on small instances. We really need to study larger instances, but we are not able to at the moment. We could use some hybrid algorithms, but that's comparing apples to oranges then, because we can also study hybrid versions of these algorithms, and we can slide the problems into smaller ones, and we run into some problems, but still, okay, this is repeated, and this is for larger sizes. So as you can see, we went up to 40K of variables, and we have still some nice behavior and nice scaling. It doesn't escape to some huge values, and it stabilizes quite nicely around 1.6, 1.7, depending on the error value. Okay, and I think this is one of the final plots for this part. This is everything combined here. So where is all the quantum supremacy papers and claims are on the shaded region, and we have to be careful for all the reasons I mentioned here. And actually what would be nice is to be able to extend this to the white region and discuss the scaling there and see what happens, because there we have larger instances. Okay, this one will be a bit shorter and simpler, because what we have is the next case study is the restricted Simon's problem. So it's just a problem of finding a period of a binary function, let's say more or less. And actually, it was solved using an oracle model, and in the quantum case, you need a linear number of queries to the oracle model. In the classical case, you need an exponential number of queries. It was in this paper that is presented here. And actually, what they did is that they had a restrict Hamming weight of this period W, and that means that the number of ones in the period is less than W, or should I say not more, because it's less than equal. Okay, and they have nice theoretical scalings. They have some results, and they implemented the Oracle on the IBM hardware using some circuits that we were able to study. And our goal was to check whether this query complexity advantage, which we don't deny, of course, the query complexity advantage is there, but is it useful? So we implemented a classical brute force solver on a single GPU. We used the same family of Oracle functions. We used the same approach to measuring time using only Oracle evaluations, because other classical work was the same. And we reconstructed their circuits with Qiskit, using the same parameters, using some transpiration to a specific architecture, using some optimization levels. We chose the number of shots that should, because they provided results only for some specific values. We extended it to a larger portion of values, and we use some timing estimates to estimate the runtime per shot and get the total runtime. And in both cases, only the Oracle execution was attributed to runtime. Let me stress again, and this is what we got. And yeah, this on the left-hand side, you have the scaling. So you have actually the quantum algorithm in this case has some logarithmic scaling, and the classical for the restricted Hamming wave has better than exponential scaling. And if you run our algorithm, you get the times reported here, because this is just raw runtime here. And the red line here is what's calculated based on the Qiskit transpilation building of the circuit and things like that. And this is the estimate on how long the circuit will run. And this shows that more or less this should be the classical brute force search, in this case, should be 2 orders of magnitude faster. But as you can see, it starts to behave badly R solver in the case of runtime for these higher values. And actually, somewhere around 60, these lines intersect. But in the original paper, they argued that noise cues them long before that. So we don't have to worry about that yet. Maybe with the dynamical circuits, maybe that will help them, help that approach. And yeah, so, and these are some fits to this function depending on the algorithm and the Hamming weight. So yeah, the price we pay here is that if we know the Hamming weight, our exponent becomes very nice, but the larger the Hamming weight, of course, the exponent becomes worse and worse. And in the general case, yeah, we would be exponential again. Okay, so this is just a summary of what I said and what I presented. So the main takeaway is that the quantum runtime is estimated to be around 2 seconds there. In our case, it's 300ths or 400ths of a second. So maybe there is the oracle call advantage there, but the actual runtimes are maybe still not there, especially if we think about specialized hardware. And as I said, we could push this further. Not use GPUs, but use something more tailored to the problem and just program an FPGA for that. The main benefit would be a lot lower energy usage compared to a GPU. Okay, and what would need to happen for the quantum algorithm to win? We would need to have some ability to simulate larger systems and more complex functions. Basically, that's the idea here. So again, we have asymptotic versus practical regime. And we really need to think about in two ways about the quantum advantage. One is what we can achieve in the asymptotic regime, but it's definitely not now, maybe in 5 years, when we have fault-tolerant computing for larger systems. And what is practically available now is what I presented here. And the final case study, this one is the quickest of all. So we go to more generalized models that don't have only 2 spin interactions, but multi-spin interactions. And there exists an algorithm called Biosphere Digitized Counter-Theoretic Quantum Optimization. And basically the algorithm runs classical simulated annealing, uses a shallow circuit on the IBM machine, and then runs assay again, starting from the output to mitigate some errors. That's the broad overview of the idea. And what we did here is just wrote our own simulated annealing that works with free-body interactions. That was one part, but the other part is that if you look at the paper that it was presented in, again, there are some assumptions as mentioned here, and it ignores lots of the times I talked about earlier, and still they didn't talk well enough about the hyperparameters that are used, and they used the time to ratio, which is more or less equivalent to the time to epsilon, but a bit different, but still the closer to one is better. And yeah, so this is another gap we found, that time accounting is wrong basically, and the time accounting is different for classical and quantum parts, and you can omit some quantum timings that you really should use, because it's a part of solving your problem, and it's hard to, I think, argue that you can just omit them, and then you cannot claim advantage. So what we did, we performed our benchmarks using SBM, using our implementation of simulated annealing, with the metrics as they used. We show how the algorithm behaves, but if you read their paper carefully, that the results they show are for specific instances, which looks like manufactured supremacy by cherry-picking some of the results that show the supremacy actually. And we go very in-depth into that in our paper. The links will be at the last slide, but this is what we found. So this is the various results from the work. The essay and the BF are from the work that we argue with, and the SBM results are ours. And as you can see, we get a better time to ratio with quite good ratios actually. So we are quite close to the optimal solution. And yeah, as I mentioned, we added the simulated annealing. And again, this underlines that we really need to say that classical quantum-inspired solvers were ignored, and the baseline was chosen incorrectly. And if we add our simulated annealing on the GPU, it outperforms on these instances. Actually, it outperforms the simulated bifurcation machine. So we get very nice time to ratios within a reasonable time. Yes, and of course, we try to run this. We try to get from these higher order instances, cubic instances, run them on the D-Wave machine, and then observe that, yeah, you cannot really ignore also the things like embedding on the machine, because it's really a cost and it introduces a lot of problems. And quickly, general lessons from both papers. So, legitimate reference. You need a good classical reference that solves the same problem natively. Be competitive and up to date. Don't go on GitHub and grab the first thing you find. Think about it. Does it really utilize modern computing hardware in the most efficient way possible? Use the same metric. Remember about hyperparameters and their tuning. Include this in your reports. For example, in the cases, PTACM is not that embarrassingly parallel as BM is. CPX requires lots of changes to the original problem, which produces overhead. But it can sometimes produce quite good solutions if you wait long enough. Small instances. You have to think about this. You cannot really say that it's scaling as in computer science when you write O of something. Some people, even I saw some papers writing O of something when it was tested on an instance which had 1000 variables. So don't do that. There are overheads, readouts, thermalization, transpilation, maybe queuing, maybe embedding. This all should be considered. And finally, you have classical accelerators that are very, very fast, very efficient. Like, well, GPUs maybe are not that efficient, but FPGAs can be, if you do it correctly. FPGAs can be very efficient. And you really have to think about that. Did you give classical computing a fighting chance? Where could quantum actually have an advantage? So we looked at some class of instances. It's discussed in the paper further that really seem to be promising for quantum architectures. But in order to really test if we have an advantage, we should have more access to more data about the simulations performed, and for example, just to have some knowledge about the actual annealing times and things like that. And things like readout times, thermalization times should be faster. Qubit counts and connectivity should be better. So more bigger, more better. Basically, that's the conclusion. And here I reiterate the gaps that were mentioned. I will not go from them again, but just remember that any theoretical advantage does not need to translate to practical runtime advantages and practical solutions currently. And future claims, just be careful what you are doing. And these are the papers. The first two are discussions with the current results. The one by leader in physical review letters is that where we showed against the D-Wave benchmark. And the other two are the other two results that I mentioned here. One is the Simons and the other is the other algorithm. Okay, and that's it. Thank you.
Thank you for a nice and practical talk with practical advices. Are there